Hello, viewers, and welcome to this episode on elegant code. This is a short video and not a series because I've tried to distill all the details of things that I've learned over the years into 5 simple principles. And hopefully, after learning these 5 simple steps, everyone can think like a pro and churn out code that is memorable. So with that, let's dive into the problem. What is the problem that programmers face every day in programming? There's obviously lots of things going on in our lives as programmers. There is technology, there is time pressures of schedules, there is PRDs and requirements that keep evolving. They're moving targets sometimes they're easy, but most cases, requirements are a tough problem. But when you think about these 3 main hurdles that we have to face in our everyday lives, time, technology, and requirements, there is a couple of approaches that programmers take. And here's a tale of 2 programmers. Programmer A, who picks up his or her requirements, and then just goes straight for execution. Very focused on execution, wants to get everything done quickly. But the result of that is that even though you try to make fast and furious, but eventually the code gets gnarly and spaghetti in such a way that eventually it takes more time and your code quality suffers. So eventually the time execution is slower as time progresses because there are more bugs, code's harder to understand, people taking up your code are not happy with it. On the other hand, programmer B went for a more balanced approach, crafting the code, thinking about execution, balancing time, and making sure that the code is written in a better way, not just the fastest possible way. So when you do that, you obviously take a little bit more time writing code, crafting code, and the result of that is that as time passes, your code's easier to maintain and it takes less and less time to modify, has less bugs, and therefore there is an economies of scale factor here that leads to you winning in the end over the other programmer, the programmer A, or you can use the conundrum of the rabbit and the tortoise. The tortoise wins, obviously, because the ability to understand your own work from the past is a huge asset. So now that we understand this problem, let's look at what the 5 principles of writing good code are, or elegant code are. The first principle is modularity. You write code that is all written in one place if it belongs together. One responsibility, and if they're similar things, they belong in one place. And we'll go into that a little bit later. But modularity is the first and foremost principle of thinking. You have to understand the code as not distributed responsibilities, but it's responsibility of one module. It's one module that holds a certain function and its data structures all in one place. The second principle is writing functions, modules, objects, whatever you like to call it, things that are pure, that do not have side effects. And by side effects, I mean environmental influences. This is actually taken from functional programming, where functions have to be pure. And if you continue that idea, the idea really means that whatever you're doing Monday and Tuesday should not change Wednesday, Thursday, and Friday, because the environment changed and your function now starts behaving differently. Those functions, those objects, whatever you have, are difficult to maintain because one has to understand what not only the code influences, but things in the environment that are affecting your code's execution. That is not a good practice. So try to write code that is pure, without side effects, without environmental influences, all in one place. Things are passed to you, and you only rely on things that are passed to you or that are contained within your perimeter. And once you trust those things that are either passed to you or within your reach, within your perimeter, then you're good. The code is more robust, it is easy to understand, easy to maintain. The third principle is meaningful comments and names. You must not write comments that are either missing, there are no comments, missing comments, bad comments. Write comments that are thoughtful, that every single line of comment means something. And the second thing is that comments, some people think that comments are really lies waiting to happen, but I think that comments do add value, but they have to be thoughtful. And they're not lies. They're only lies if you don't keep up with them. When you change a piece of code, make sure you're also updating the comments. That's the way to prevent the lies from happening. The other part of this principle is naming. And the way you name your objects, methods, variables is very important. And we'll cover that in another slide. But naming and commenting is more of a stylistic part of your code, but it's fairly important. And by looking at somebody's code, by looking at how they name their variables, by looking at what kind of comments they have left, it can make a huge difference. The next principle is backwards compatibility. And it's a huge principle. It's very important for writing good code. Backwards compatibility is something that one has to deal with in writing production code, and you will be asked, the requirements today are that you develop something, and tomorrow the requirements change and add features and more features and on and on and on. But how do you make sure the code that I wrote yesterday and a month ago and a year ago, what is the value of that code? Is it totally worthless? Or is it written in a way that I can actually count on that code still being okay while I'm extending it? So we ask the question, what can remain invariant? Where are the contracts? What is something that I can hold on to while the change is happening? And as long as a programmer, you understand that there is a contract, there is something that is very important to keep fixed and not moving, then you can write code around that fixed part, and that makes your code more robust. The final principle, and not any less important than the others, is writing good test suites. You must think about writing unit tests and test cases to cover all possible scenarios for the inputs that are coming into you, and make sure that in all the cases you know what will happen and you can predict all the things like nulls coming in, somebody entering bad data into your code. You must try to think about all those things. In fact, testing has become so popular these days. There's approaches called test-driven development where you write tests even before you write code. And so testing has gained prominence in today's world, where the code comes second, but tests come first. So these are the 5 principles. Now let's dive deeper into all these principles and see with examples maybe, and digest them better so that we can remember them in future. So here's the first one, modularity, which I said was the first and foremost principle. And the example I've chosen is writing a program for chess, let's say. So modularity is important, we understand that. But when you think about chess, if I'm a procedural programmer, I just see chess as a big, giant, data structure and code. And I could write it that way, but perhaps it'd be very difficult to maintain. And somebody trying to change it might feel like they have to take some time, digest the code over a week, and then start making changes to your code. And even though they make changes, they find it difficult because they touch something and they break something else. So how do you tackle this? The way we tackle this is through modularity. And you can think of the game of chess as, yes, there is a board. At high level, there is a board, and the board is made up of squares. Each square has an X and Y coordinate. You can designate a box or a square as having a color, right? It's white or black. And then if a piece is on it, it has a state. So you know that this piece located, this box or square located in this X and this Y is of this color, and it has this colored element present on it. It's it's a white king on it, or it's a black queen on it, or a rook on it of a certain color, so on. So the board and the squares are different. A square, you could have multiple squares on a board. So board is inherently a different object. It's made up of these squares or boxes which have their own properties. So I could think of box as a module, and everything within a box could have, by similarity, similarity gives them cohesion, which is they belong together. The other thing in the board in the game of chess is pieces. And the pieces, there is black and white pieces, and there's different kinds of pieces, and they all move differently. So I could start with a piece which has a certain well-defined functionality, and I can extend these pieces and build other pieces like king, knight, queen, pawns, etc. But I have certain common functionality, like can this piece move from X to Y? And we'll cover this principle in the next slide. But in general, once you sit down and define the object structure, the object model that underlies this problem, you can break the procedural code down into this object interaction instead. And if you break this into object interaction instead of procedural code, which just says stuff happens and I do X, Y, and Z and I go down this branch. No, this code is now broken down into objects and how the objects interact with each other. When the user moves something, it's the box that is interacting with the piece, which is interacting with the board, and then you can easily see that where you're moving and which function is getting called. And when somebody tries to debug your code, they're just looking at, let's say, a piece, and they're trying to debug why the king is behaving this way and some bug is there. They can see that your definition of the king's moves are incorrect. They're not worried about the knight's moves. They are worried about the king's moves. And moreover, if the piece functionality is wrong, like the move is not been defined from X to Y and you need to extend it, you need to add more inputs, parameters, you need to define that in the piece. You're not worried about how the king will move or the knight will move and so on. So this limiting the scope of what you are about to do in a module gives you the simplicity. And that simplicity helps write better code, easier to debug, easier to understand. The next principle that I'd like to discuss is backwards compatibility. And that's another very big principle of writing elegant code. Now, like I mentioned earlier, before you think about backwards compatibility, the underpinning of backwards compatibility is what remains the same. That something has to remain the same for you to be backwards compatible. There could be a contract. There could be something that remains the same. For example, if you take a program and improve its performance, as long as you didn't change anything on its interface, other objects relying on that can use that contract to say, hey, I can still use the new and improved function or object because there is a contract which remained the same. And that allows you to hook on to that function or an object and do the stuff that you are asked to do. Another example as shown here is accounting. And when you create, a bank creates accounts, the account has some underlying contract, like there are methods that add, withdraw, there's terms that are associated with the account. And you can create, let's say you have checkings and savings today, and these are working, customers are using it, and tomorrow you add money market, CD, brokerage, and so on, and some other fancier accounts. The thing is that it should not break the code for checkings and savings. When you create money market, it should not break checkings and savings, and you can extend. So sometimes it's called open close principles, principle, that you're open to add more stuff, but you're close to modifying stuff. So that way you can keep the checking and savings accounts okay while you're adding money market, CD, brokerage, etc. So when you think about this, is an important and very fundamental principle that creates reliability, stability in your code. That you're not breaking the code from yesterday, and you're adding more code. And so think about contracts. Think about things that remain the same and do not change. And as long as you think about those things and plan them well ahead in time, you will produce code that does not change easily. Don't just jump, like the first programmer in our example, don't jump to writing your code. Think about the contracts. Think about the responsibilities. And if you think for an hour and you have to write the code for a day, at least think for an hour. And if you do that, you'll be able to write code that saves you time in the long run. The next principle, I guess lower in the priority of things, the order of things, is naming. And naming is important, however. So I give you two examples here. On the left side, the first example shows you some sort of calculation happening with ABC as my inputs. And I return some function which looks like, yeah, I think I understand it, but doesn't really make sense to me if I have to debug it. I do not know what this function really is. I don't have any context for this function. But on the right side, if you see, if I say it's a compound interest formula and the inputs are principal, rate, and years, then you can see very quickly what they mean, what the formula means. And if we have to debug it, it's very easy to understand. The second example is where I have taken a for loop, but the for I'm using just a variable I. The iterator is I, which is very common, and then I index it and I print something. On the right side, I've written it differently, where I've used the variable month to represent the value, and then instead of calling the variable K, I've called it monthly gas and the utilization for that given month, and then I print that utilization was of monthly gas. So it's very easy to understand. The code itself, without any comments, is telling me that this function is computing and printing utilization for monthly gas for all the months from 0 through 11. So that's naming for clarity. You must try to use names that mean something so that other programmers, when they read your code or you read your code a year from now, the variables will mean something to you, and probably there'll be a breadcrumb there for you to trace your path, and that helps you along the way. Then we come down to comments, and comments are very useful if written correctly. And like I said before, the comments could also be lies waiting to happen. If you write your comments and then keep changing your code and forget about your comments, or you write meaningless comments, they are just lies and nobody likes those. So the way I've shown that here is that if you look at the left side here, I've used a function diff time, and there's two parameters a and b. I return a minus b. On the right side, the comment says, yes, this calculates difference between two time samples, and the arguments are time after and time before and are in seconds as a floating point variable. It also mentions that there is a caveat that precision is lost after 7 decimal digits in the input. If more precision is needed, try this other function, which is very useful. It tells you right off the bat that you must use the function in the limits that it has, the caveat that it has. And if you do that, then you'll get the precision and the accuracy as you need. So Right off the bat, this comment is very useful. And if I read this comment, I can appreciate the fact that the programmer took the time to leave that piece of breadcrumb for me. And then not only that, the naming in the previous slide, you can see the naming. Instead of just calling it A and B, I can say time after time before. And the return is time after minus time before, and which is good to understand. So naming conventions and comments here play a big role in making the code more readable and therefore easy to modify when the time comes. So to conclude, programming is about 100 years old now. I think the earliest thoughts about programmers and computers came around in the 1930s. So programming is an old art and science. Languages keep evolving. There's plethora of languages. People have programmed in C, C++, C#, Java, and then a whole bunch of new languages like Python, Ruby, JavaScript, all kinds of languages, and there's no end to these languages. More and more new languages are being born, and at a faster rate than before. So languages keep evolving, but what grounds us into quality is the principles. And the principles of design that I mentioned here are the solid principles which every programmer must understand, despite of the language that you're writing your code in, despite of the way in which you're crafting your code and how fast you're delivering your project. It may change. You have to adapt because time is the essence. Your manager is not going to give you infinite time to do stuff. So you have to understand the pressures of time, moving requirements, and the technology are always a challenge. But if you can write your code using these principles, then your code is built to last and it's easy to modify. So there you have it, viewers. That's the video which summarizes my thoughts on the principles underlying elegant code. I hope you enjoyed this video, and if you did, do give me a thumbs up and please leave me comments. And if you'd like to see more content like this, then please subscribe to my channel or let me know in the comments also what you would like to see. And until next time, a bientôt. See you soon. Bye-bye.